So as we begin our lecture on lightning, I want to introduce you to Roy Cleveland Sullivan. He is a Shenandoah National Park, that's in Virginia. He's a park ranger, and this guy currently holds the world record for the most times being struck by lightning, each one documented, and surviving them all. He's got a pretty interesting life story here because over about 35 years, he was struck 7 different times. He was hit in the leg, he was hit in the foot, he was hit in a vehicle, which is quite rare. He was hit in his ranger station. One time he was hit in the head and amazingly survived it, but it set his hair on fire. After that strike, he started to carry around a small pitcher of water with him everywhere he went, so in case he got hit again, he could put his hair out. Ironically enough, the next lightning stroke hit him on the head, set his hair on fire again, and he was not conscious to put his hair out. But what's amazing is this man survived 7 different lightning strikes. And that's an important thing to be talking about, especially about the fact that it is a man. And that's what I want to begin with here. You see, you're looking at a graph here that shows you U.S. lightning fatalities or deaths from 2007 to 2017. And when you look at this, we've got icons here that represent male, female, and also they're color-coded. And basically, the overwhelming majority of lightning victims are male. Now, there's a lot of reasons that this could possibly be the case, but I just want to bring up one story as you look at this figure. I read in the New England Journal of Medicine several years ago an interesting article, and the article basically went like this. The title says, "Music Players in Lightning Risk." You see, there was a story about a man who was jogging in a thunderstorm and suffered burns to his chest and on his leg where he was wearing his iPod. Now, when they basically went and saw this guy after he was struck, he had these burn marks that ran up his leg, across his chest, along the cord for his earbuds, and eventually across his face into his ears. When the lightning struck this guy, the metal cable helped conduct some of the electricity. Now, what was crazy was because it went into his ears, when that electricity passed through his head, it made the muscles in his jaw clamp down so tightly that it broke his jawbone and shattered his teeth. That's incredible. He was thrown 8 feet from where he was struck. He eventually lost 50% of his hearing, but thankfully he survived the event. Now, what's the moral of the story? Now, you might be thinking, gosh, I should never wear my iPod if I'm out in a thunderstorm. No, 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 no. Your iPod is not a risk. It's not a risk factor for you getting struck by lightning. You see, it was the very first thing I said. The man who was jogging in a storm suffered burns to his chest and leg when he was struck by lightning, and he broke his jaw and his teeth. You see, why did this guy decide to go running in a thunderstorm, putting himself at risk? You see, I bring that up because I'm going to show you several years here of lightning fatalities. And each one of these each one of these charts I'm going to show you is color-coded, blue or pink to denote male, female. Now, look at this. Activity, location. We can clearly see here the differences. Where are the men? Look at this. Had been fishing, open field, farm, under tree, fishing, soccer, under tree, fishing, near trees, under trees, camping, beach, fishing, sailing, being carried, walking to a boat, near tree, under tree. And there's a very clear signal. Where were the women? On a beach, family outing, under a tree, picking berries, outside installing a watering system. Still, there's overwhelming statistical evidence here of male being struck more often than female. Let's go to the next year, 2013. Look at it again. Activity. Fishing. Look at this. It's just this constant theme here. In a barn, under tree, near tree, under tree. You're seeing the same kind of persistent behavioral choices here that are making people more susceptible to being struck. Kind of a tragic one, though, right here. Look at this one. This is scenic overview. This was where we had 2 people that were on their honeymoon that were both struck and killed. Now, this is 2014. You're going to see a very similar pattern here with where people were when they were struck and killed by lightning. And also look at this. Of all the deaths in 2014, of which there were 26, just five were female. This is 2016. You see the same pattern repeating over and over. And please feel free to pause the video, stop and look at these images just to kind of see what people are doing when they were doing. And I just want to make one other point. Age doesn't matter here. Look at this. We had a 5-year-old and an 8-year-old, and next to that a 71-year-old, a 70-year-old, 72. So this spans the entire, lifespan of humans. 2017 deaths, this is the most recent statistics available. We had 16 total fatalities. One of them was a female. Where was she? In an open field near a tree. but you can clearly see the locations of people when they're struck and killed by lightning. We have to keep that as a central background theme to this entire lecture, because I'm going to teach you how lightning forms and how it strikes and what it can do. Remember, when it comes to safety, there are certain things you got to make sure you're doing in order to stay safe from lightning. So let's talk about weather fatalities. Over the last 30 years, that would be the yellow bars on this graph, we know that death from heat-aggravated illnesses leads the way. So you can see right here, 134 deaths is the 30-year average. What's number 2? Flooding. What's number 3? Tornadoes. That's helped spread along by the huge event we had back in 2011, which really rose the tornado fatality count. After that, though, look, we're kind of in this territory where both hurricanes' 30-year average and lightning's 30-year average are about the same. But technically, lightning ranks 5th on this list. But still, it's a killer. It's a big-time killer. And when you hear me tell you a few minutes about the number of strikes we have in the U.S. each year, you'll see that it's amazing that that number's not higher. When it comes to lightning fatalities, though, check out this figure. 1940 on the x-axis all the way to 2017. Number of deaths on the y-axis. This will be one of the only charts that I show you where there is a very clear exponential decrease in the number of fatalities. Still, what are the statistics? Well, the 50-year average is about 600 people in the United States are struck annually. But only about 60 of them die. That's the averages over the last 50 years. So when you see that number, what I want you to remember is 90% of people that are struck by lightning survive. And this is a testament to medical technology. This is an understanding of what to do when someone is struck. People now know that the moment they're struck, it's not that they're going to be electrocuted if they go touch them, but instead they need to check for a pulse, and they need to check to see if that person is breathing and has a pulse. Then you can perform CPR. You see, in the past, when not everybody knew CPR, we had more fatalities. In the past, also, we didn't understand that even up to 6 to 10 hours after a person was struck, they could still have a heart attack. You see, that's how you die from lightning strike. You're either killed instantly through electrocution, or you died later from ventricular fibrillation, which is basically having a heart attack. Now, thankfully, our 10-year average is at 27. So this is what it looks like in terms of lightning fatalities. Next, what is the cost per year for lightning strikes in the United States? Well, I went to Hartford Insurance Group and also contacted State Farm, and basically the industry-wide number for insured payouts is somewhere between $4 and $5 billion. And that makes us one of the biggest insured payouts of all of our different types of severe weather. So $4 to $5 billion. Okay, before we get into all the really nasty parts of lightning and what it can do, I want to tell you about something positive that lightning does. You see, when lightning starts forest fires, like what you see here, it turns out this is a very natural part of forest life cycle. So when lightnings burn forest, this is a good thing. This is actually a rejuvenation of the forest kind of biome there. Turns out, though, while lightning burns more acreage annually in North America, humans start more forest fires than lightning does. But I just want to tell you something. When lightning does start a fire like this is actually a normal part of the life cycle of a forest. But when we talk about what the lightning strike is, here's some of the basics. Ready? It's a giant spark. That's all that it is. But this spark is powerful. It can contain well over 1 billion volts and well over 30,000 amps. Now, for perspective, my computer right now is plugged into the wall in my basement where I'm doing this recording. That wall outlet produces 110 volts and 15 amps. And you know what would happen if you stuck a fork in one of those? You get a real nasty shock. Well, look at these numbers. 1 billion plus volts, 30+ thousand amps. How big is a typical lightning strike? About 5 kilometers long, so that's a little over 3 miles. And it's typically about the spark itself is about the width of your thumb, which is about an inch, 2 to 3 centimeters. Now, it's these next two statistics which are amazing. On Earth, every day, around 9 million strikes. That's 100 lightning strikes per second on Earth. And that's an incredible number, which means lightning is a very regular part of the balance of kind of the electric field between the Earth and its atmosphere. And finally, when a lightning strike occurs, it'll heat the air up to 30,000 degrees Celsius. That's 54,000 Fahrenheit. And that is 5 times hotter than the surface of the sun. That's my picture you've been looking at there in the background. That strike was about 30 yards from me, and it was absolutely incredible, and it scared the daylights out of me. Okay, I want to show you this really cool animation. This was from years ago from some of the US astronauts, and check it out. Here we are on the International Space Station. You're looking down, and this bright blob you see here, that's Dallas, Fort Worth is actually underneath this thunderstorm. You can see all of the different lightning strikes around this particular big city in the American southern state here of Texas. Amazing. You can't count them. There's too many of them to count just if you kind of time to do this in your brain. That's how regular lightning is, because we're just looking at one little corner of the world here and seeing so many strikes. All right. In the United States, because we have a national lightning detection network, we've counted that on average, there are somewhere between 20 and 30 million cloud-to-ground lightning strikes per year in the United States. You're watching an animation here showing you those strike locations from some nasty storms from 2017 that were going through parts of Arkansas, Alabama, and Louisiana. In total, if you look at it, there were 17,000 strikes in this sector, 2,000 strikes in this sector, and nearly 1,700 strikes in this one. So when you add all of this up, we're talking about over 20,000 lightning strikes in the last 2 hours alone. So it's incredible to see that. But what I want to talk about is how can we make maps like this? Well, here's what our National Lightning Detection Network sensor map looks like. Now, there are actually multiple lightning detection networks all over the United States and the world. I'm just going to show you one because they all kind of work in a similar fashion. But I also want you to know we can measure lightning from space as well. We'll see that in a few moments. Well, let me show you. We got all these sensors placed all over the country, and these sensors are very sensitive to these giant electromagnetic pulses that kind of come off of a lightning strike. So it looks like this. Imagine you got your lightning detection sensor, it's over there, and lightning strikes right there. When it strikes, it sends out this large isotropic blast of electromagnetic radiation. And when that passes over the sensor, it trips the sensor. Basically, the sensor is like an AM radio wave tower. It's sensitive to that kind of wavelength of light. And then the wave keeps going on past it. Now, how does this work? Well, if we have a network of these sensors, we can measure the time it takes for or between when each sensor detects one of these electromagnetic pulses. So for example, if the lightning strikes right there where the X is, and it puts out this huge pulse of electromagnetic energy, it hits the sensor in Indiana first, the one in Missouri second, and the one in Wisconsin third, just based on distance. We can then use the time that it tripped the sensor and construct circles, and where the circles intersect, you have the position of the lightning strike. This is basically how GPS works. We are using the electromagnetic blast of a lightning strike to basically GPS its location. Pretty neat how we do that. So each one of the dots you see here, we have a vast network of sensors, and they are each kind of picking up on the location of a lightning strike. Really neat to see that. We then color code the lightning strikes according to age. So we want to see where the storm has been. So we make the strike as it's been in the system longer. So the older the strike, we color a darker color here. So the white ones are brand new, and you move toward the reds. Those are just old strikes. So the red ones used to be white strikes a while ago. Okay, just to show you we can measure this from space, this is our GOES-16 satellite capturing this amazing day where we had a dry line moving out of parts of New Mexico into Texas, kicking off a huge line of storms, and then a thunderstorm complex coming out of Louisiana, Texas toward it, and they kind of collided right there in the middle of Texas. But this is what it looks like to observe lightning from space from our geostationary satellites. So because we can do that, we can also make maps around the whole world of where lightning happens. So this is a lightning flash density map, and it shows you where lightning has struck all over the planet over a given time period. Now, clearly, some of the most active spots for lightning on Earth are going to be right here in the rainforests of our planet. So we can see, especially here in Central Africa, but also in the Amazon, you can see them also getting down here into parts of Paraguay. This is southern Brazil, northern Argentina, very active. Of course, the southeastern part of the United States is very active for lightning. And also we can see up here in the foothills of the Himalayas, getting down here to Southeast Asia. And then, of course, all in the huge island network that is just south of Southeast Asia that sits over here in the Western Pacific and the Indian Ocean. So we can clearly see where lightning is. But if we talk about this with respect to the United States, I want you to remember this one bullet point, okay? Florida is the lightning capital of the U.S. Florida has thunderstorms year-round. Florida has thunderstorms year-round, and as a consequence of that, plus a very high population, we see that Florida has twice as many fatalities as the next state on the list. So 477 deaths between 1959 and 2014. Number 2 is Texas at 218. You can see that clearly the states that have the most lightning fatalities have high populations and are close to the Gulf of Mexico, which is the primary source for the moisture in our major thunderstorms. You can also see the West Coast, much lower frequency of thunderstorms. Therefore, you can see much smaller numbers. But Florida takes the cake. It's the lightning capital of the United States. So here's a fun question, all right? If all of the energy from a single bolt of lightning could be captured, how long could this electricity run your house? So let's just think about it. You think it'll run it for 6 hours, 6 days, 6 weeks, 6 months, or 6 years? Think about your answer for a second. All right. Capture all the energy from a strike like this. How much do we have? Well, check this out. Here's just a quick calculation for lightning power output. Ready? For a standard 5-kilometer lightning bolt, it contains somewhere, let's just call it between 15,000 and 30,000 amps. That's a lot. Total energy content will be somewhere between 1 and 10 billion joules. And by the way, some of our biggest strikes can get over 300,000 amps. So we're looking at a pretty conservative lightning strike here. But this is what I want you to remember. Only 10 million of the 10 billion joules in a lightning strike are electrical. The rest of that energy is heat. Now, what does that mean? Well, when you pay a bill every month to the power company, you're going to be paying them by the kilowatt hour, which is a unit of energy. So 1 kilowatt hour, as measured by the dial outside on your apartment or house, is the equivalent of 3.6 million joules. Okay, so a typical small house in the United States maybe consumes 500 kilowatt hours of electricity per month. That's 1.8 billion joules. Now, one bolt of lightning could therefore power one house for about 5.5 months, or roughly 6 months. If, and this is a big if we could store all the energy from the strike. But in reality, a fraction of that energy is electrical. If we only got the electrical part and we could somehow store it in batteries, we'd only have about 6 hours worth of power. So while lightning strikes are very, very powerful, most of their energy is heat. And that's how they're able to heat the air to 54,000 Fahrenheit. That's 30,000 degrees Celsius. Now, interesting kind of bit of movie trivia history here. I got a picture here of the DeLorean from the movie or the trilogy Back to the Future. Now, spoiler alert, this is the car that Michael J. Fox uses to go in the first movie back to 1955. And then once he's there, he's trying to get back to the future, hence the name of the movie. Now, Doc Brown, the inventor of this car, needs to figure out a way to power it because once he goes back to 1955, he doesn't have the fuel source he needs. He says, well, the car needs 1.21 gigawatts of electricity. Now, 1.21 gigawatts of power is not how we'd say this because we don't say like your iPhone is measured in gigabytes. No, it's giga, right? So it needs 1.21 gigawatts, so billion watts. And the question is, can lightning do this? Well, I'm going to tell you something. They should have done their calculations a little bit better. A typical positive polarity lightning strike, if they were to actually try to channel that energy all the way into the flux capacitor, which apparently is all you need to travel time, you would have ended up getting around 100,000 times too much power. So 1.21 gigawatts is not that much power, okay? Just thought I'd kind of throw that in there in case you're a movie fan, all right? Okay, let's dig into how clouds become electrified. Here we go. Pay close attention to this. A quick review of some of the things I need you to know about electricity. First, when we think about an atom, remember that in the center of the atom you have protons and neutrons. And those protons have a positive charge to them. Orbiting the atom, which is the kind of the way that we diagram out atoms. They don't really look at it, but that's the way we think about it. Orbiting them, and this cloud is we have these electrons, and they carry with them a negative charge. Now, any atom that has too few or too many electrons compared to the number of protons is called an ion. So this is an unbalanced atom. Electrons, remember, are mobile, which means electrons can move from molecule to molecule. You stand up right now and go walk across a shaggy carpet dragging your feet. You're picking up countless numbers of electrons. Protons are not mobile. They have to move with the atom. And therefore, if you pick up a proton, you've picked up the whole atom. Finally, in that top panel here, like charges repel, opposite charges attract. You probably remember this from playing with magnets as a kid. Okay, 4 other definitions. 1, what's electricity? We're just going to define it as the flow of electrons. Okay. 2, what's an electric field? It's an attraction between charge centers. When you separate positive charges and negative charges, they're attracted to one another because opposite charges attract. What's a conductor? Well, the really good conductor is a material that contains lots of movable charges, like silver, I think, is the best, but copper wire is very good. Water is also a good conductor. And what's an insulator? Anything that wants to resist moving charges. And what's interesting is air is an outstanding insulator, which means it's very difficult to pass electricity through air. That's why lightning strikes are so powerful. Okay, here we go. This is how a cloud becomes electrified. Ready? I got a tree sitting on the ground down there. Sorry I had to draw this in PowerPoint, but this is the best I could do. Here's a mature thunderstorm. So here's the base of the thunderstorm. Here's the anvil at the very top. So this stretches through the entire depth of the troposphere. So this is clearly not to scale. This would be an enormous tree compared to the size of this thunderstorm. So we're not looking at this at scale. When we have a mature thunderstorm capable of producing lightning, we find that it breaks its charges up into two groups. A bunch of negative charges tend to accumulate at the bottom of the cloud, and positive charges near the top. Now, because of that, tall objects near the surface tend to accumulate positive charges. And I wrote down there why. It's because they're attracted. These positive charges are attracted to the negative charges at the cloud base. Also because the cloud base is so negatively charged, because like charges repel, this huge electric field, which can be 1 million to up to 3 million volts per meter, will push away the negative charges on the ground. You see, that's why the tall objects tend to take on a positive charge, because we've moved all the electrons out of the way. So it's becoming positively charged kind of by default, by getting rid of electrons. They're kind of spread away, and we call that image charging. Now, when that electric field builds up, it is powerful. If you were standing in that electric field, your hair would stand up on end. Like something like just straight up as if you were like at a children's museum touching a Van de Graaff generator. Now, even if you don't have hair, you're going to feel this. But the question I want to answer, this is why we went to this next slide here, is why did that even happen? Okay, thunderstorms, the big clouds that they are produced, the thunderstorms are produced from, are made of updrafts. That's that red arrow. Now, inside of a thunderstorm, you have a mixture of different water types. You have liquid water. You then have supercooled water. You also have frozen water, which we call ice, and it's the ice that I want to talk about. You see, when ice freezes, it doesn't always freeze in the same shape. You may think it freezes like a snowflake, like you see right here. But in reality, it can freeze in all sorts of different shapes. Dendrites, like you see here, but it could also freeze in columns. It could freeze into needles. It could freeze into plates, and all sorts of other shapes. And sometimes it'll freeze into small hailstones called graupel. But in order for a thunderstorm to even be produced, which means to make lightning, we have to have this crucial ingredient of ice, and this is why. Okay, in the presence of an updraft like this, we're going to watch these two particles of ice, one forming like a piece of graupel, the other forming like an ice crystal like you see down here. We're going to watch them collide. Now, before they collide, look at this. They're neutrally charged. There's the same number of negative charges as there are positive. But what we've discovered in our cloud chambers is that ice crystals, when they form like the one you see down here, well, they tend to wear a lot of their negative charges all along the periphery. And that means whenever they come into contact with something, just like if you walk across a really shaggy carpet and you touch somebody with your finger and you shock them, well, this ice crystal is going to be very good as it floats up in this updraft of giving up these electrons it wears all along its edges. Watch this. Ice crystal rises and eventually collides with the piece of graupel. Now, why does that happen? Well, the graupel's heavy. It's falling. The ice crystal's light. It is rising. And when they collide, see this electron right here? It's going to go into the graupel. Now, what just happened? Well, the ice crystal giving up an electron is now net positively charged. The graupel, which now is an extra electron, is now net negatively charged. The ice crystal is light, large surface area, not very dense. The updraft blows it to the top of the storm. The piece of graupel, which is a big piece of spongy ice, kind of think of like those little tiny ice cubes you can get sometimes when you buy, like a soft drink at a fast food restaurant, okay? That soft spongy hail is heavy, and it falls down. It comes down in the atmosphere in the storm with its net negative charge. And this process happens countless numbers of times within the thunderstorm. The ice crystals collide with the hailstones of the small, soft, spongy graupel, and there's an exchange of electrons. The negatively charged graupel falls to the bottom of the storm because it's heavy. The positively charged ice crystal floats to the top. And we get an electric field. We get charge separation. Positive on top, negative on bottom. When that happens, we've separated the charges and all they want to do is equalize. And that's how we get lightning. Now, there are 4 common types of lightning. we have in cloud. This is where you have a negative charge in one part of a cloud arcing with a positive charge in another part of the same cloud. You can have cloud to cloud. This is where the negative part of one cloud arcs with the positive part of another cloud, not the same one, but another one. You can have cloud to air. You can even have electrical discharge into the free atmosphere around the thunderstorm. But the one we're going to study, that's the one pictured here really well on the bottom. We're going to talk about the cloud to ground lightning strike, this right down here, because it'll be this one that has the highest probability of killing you. Now, remember earlier I told you about all of those lightning strikes we have every single day, every single second? Well, 80% of all lightning strikes are in the cloud. 20% are the cloud to ground. When you see that number 20% though, well, I want you to know this. The 20 million to 30 million strikes that we measure each year in the United States, I'm only talking about the cloud to ground variety, these. I'm not even counting 80% of all the strikes we have. So moral of the story, lightning is extremely frequent in the Earth atmosphere system. Now I got to take a moment here and come back to a topic we addressed just a few moments ago, trees. You need to know that statistic. 14% of all lightning fatalities are people that are standing next to trees. Now, if you're standing next to a tree, there's a couple of things we've kind of learned in the lab. If the tree bark is wet, we tend to find that the lightning, when it hits the tree, stays in the bark. One of my former students, Ethan, took this phenomenal picture of a lightning that struck this tree. See the large scar down the middle? Well, that meant that because the tree bark was wet, the electricity stayed in the bark and tore a nice line through it here, certainly burned it. But the tree will likely survive this particular event. Remember though, don't ever stand next to trees. My dad knows this lesson very well. This was an animation of lightning back on June 25th, 2014. I will never ever forget this day. My mother called me very early in the morning and told me, "Eric, are you sitting down?" Well, you know you hate to hear someone say something like that on the phone. I said, "What happened?" She said, "Your dad was struck by lightning this morning." And for a moment there, I just panicked. And I said, "Did he survive?" Because I knew the statistics. I knew that 90% of people that are struck survive. He says, "Yes, we're on our way to the hospital right now." I said, "Where was he?" He says he was outside getting in the car. See, June 25th is my mom's birthday. My dad went out early in the morning to get the car before the thunderstorm was there to basically get my mom in the car before they left so they could go have breakfast. Well, on his way out, he was in north central Wisconsin on vacation. And that little strike right there, the one right out ahead of that storm system, hit the tree, ran down through the bark, and went right into the root that my dad was standing on. And when it hit him, it went right up into his leg and threw him about 10 feet against the cabin that they were staying in. Now, my dad, thankfully, did not have a heart attack. You see, normally when this happens, if you don't have an instant heart attack or you're not electrocuted, they have to monitor you for at least 6 hours. And that's what they did to my dad. They basically took him to the hospital and they monitored his heart to see if he had any sort of irregularities. After that, they released him and we kept monitoring him for the next few days. And he was perfectly fine after this event, although he had some really cool burn marks on his legs. Now, I'm going to tell you something about this, though, as you've been watching this animation, okay? My dad was not necessarily doing something that was risky. In fact, he was doing something to be very polite for my mother. Yet still he was struck. He was under a tree. In the north woods of Wisconsin, that's almost unavoidable, but still pretty crazy to hear. The last thing I want to tell you about my dad, for about 6 months after he was struck by lightning, my dad displayed at times some symptoms of depression. Now, he wasn't depressed. He didn't act depressed. He wouldn't have gotten a psychologist to write off that he was depressed, but at times he was acting that way. Unexplained, couldn't quite figure it out. But that's a very common thing we hear about lightning, people that are struck by lightning that survive, is that they often have depression-like symptoms for a time period after they're struck. Trees, though, please stay away from trees. Thankfully, this didn't happen. You see, when the tree bark is dry, sometimes the lightning likes to go right into the center of the tree where all the water and the sap is. It superheats it and blows the tree apart. I am so thankful that this did not happen because this would have killed my father. In fact, here's another view of a tree that was struck by lightning and it blew it apart from the inside out. So wet bark, we've generally found that the lightning tries to stay in the bark. Dry bark, it tends to go right down the center and superheat the thing and blow it apart. Incredible to see that. Now, this image is one of the most famous of all images when it comes to lightning strikes. Incredible that this was captured. You have lightning striking a tree, but you see the delicate parts of the strike, like a step leader over here in the upper left. the positive streamers coming off of the tower and off the top of the tree, and the return stroke, which is the big bright flash that you see here. We got to talk about this. We got to understand how and why this happens, because we now know why clouds and how clouds become electrified. The strike is the result of the massive buildup in charge. Another fun question for you. In which direction does the bright flash of light that you see during a lightning strike travel? So when you see lightning, which way does it go? Does it go A, from the ground to the cloud, so that's up, or does it go B, from the cloud to the ground, which is down? What do you think your answer is? Well, I think we should answer this one because I get asked this question all the time. So here we go. Remember our thunderstorm from earlier? Here it is again. I'd like to talk with you about a type of strike called a negative polarity strike. This is 95% of all cloud-to-ground lightning strikes behave this way. And this is how it begins. You see, the first part of a lightning strike is called a step leader. And a step leader happens when some of these negatively charged particles here at the base of the cloud begin to search out a path of least resistance to the positive charges that are on the ground. Okay? When this happens, it does it in a very step-like or fork-like pattern. Watch the animation because it looks just like this. Now you can see each one of these leaders went out and tried to find a path of least resistance. But only one of them is actually coming toward the tree where the positive charges are. So it's kind of like they're blindly hunting for those positive charges. Now, you can't see this. It doesn't have enough energy in it to really make the atmosphere glow, and therefore you can't see it. But as these electrons are coming down here, these negatively charged particles are coming down here, the tree responds with its positive charges and sends up a little positive streamer. See the plus signs I just added there? This positive streamer moves up to meet the negative charges coming down. You won't see any of this unless you're very, very, very close. But once they touch, we open up a channel. We get what's called the return stroke. At that moment, a lot of these negatively charged particles at the base of the cloud go rushing down this channel. And as they go rushing down that channel, the current and the bright flash in the ionization goes back up, just like that. So 95% of all cloud-to-ground lightning strikes that you've seen, they all go, the bright flash at least, goes from the ground up. Now, why can't we see this? Because it happens so fast. You see, the lightning strike, as it occurs, takes just microseconds. You're watching this video right now, your brain is interpreting, if we want to think about this in terms of film, you're watching this at about 30 frames per second. Imagine you had a brain that could process things in millions of frames per second. Then you'd be able to see it. But that would be an overwhelming amount of information for our brains. Now what's neat is this. After your step leader's gone down and your return stroke has gone back up, you can often get what are called multiple return strokes, where basically any leftover charges here at the cloud base will go right back down the open channel. You get another return stroke. More electrons down the same channel, another return stroke. And this can happen several times. In fact, I think the record that we've measured is 21 or 22 times. So step leader comes down with electrons. Positive streamer jumps up to meet it. The current runs right back up the channel. That's the bright flash we see called the return stroke. And then the whole process can repeat itself. Now, take a moment, pause the video, and see if this makes sense. And then watch this with me. To prove this point to you, I'm going to show you some of the research from Tom Warner. I'm so thankful that he shares his videos with us. This particular video is shot at 9,000 frames per second. And you're about to see this whole process happen. Are you ready? You would not see what we're about to see at the beginning. That is invisible to you. Those are the step leaders. And that one won. Watch right down here. See the step leaders coming down? Only visible to this camera. The one that got there first, the moment it hit, all the negative charges rushed down and the current went right back up. Watch it again right here. See where the bright flash starts? It's at the bottom and goes up. One more time. See, I'll slow it way down. Return stroke right now. There it goes. Bottom up. That's 95% of all cloud-to-ground lightning strikes. Isn't that awesome? Let me show you some more. Check this out. This is shot in nearly pitch dark. You can see how sensitive Tom's cameras are. Ready? Here we go. There's some leaders. See them up there? Searching, searching, searching. Which one gets there first? That one. And that is the return stroke. Watch this animation over here. This one's kind of fun. See this antenna? Here we go. Ready? I got to start and pause this one. There we go. Here comes the stepped leader. See them coming down? This is the positive streamer going up. When they meet, you get the bright flash. In fact, it saturated the camera. That's amazing to see, though, isn't it? Let's take this one back here and show it to you again. There it is. See the positive streamer going up? The subleader coming down? When they hit, bright flash. Check this one out down here. There's one leader. Ready? Where is it? There it is. See it? One leader searching, searching. Watch it right over here. Searching, searching. Looking for the positive charges. Getting closer, getting closer. There they are. There they are. Boom. There is the return stroke. And I think we better watch this video here in full screen, okay? Now check this one out. In this particular case, this video starts at 1:37:03.8 a.m. Here we have our negative leaders coming down. See them? And eventually one of them is going to get to the ground first, and that will be the, there it is, that's our first return stroke. Now as we're watching this video, which is shot at 9,000 frames per second, look at this tower here, and this tower here and here. Do you see how they're sending their negatively charged leaders up? You see, in this case, you're looking at a positive polarity strike. Positive polarity strikes go the opposite direction. So technically, nobody got the question wrong asked a few moments ago. This particular channel right here, watch, it's going to get lit up 16 times. 16 return strokes. Ready? They're getting ready to start. 1. You can just keep counting them if you want. But 16 times that one channel is going to get struck. Notice that each one of these strikes is coming from the cloud into the ground. See, that's a positive polarity strike. So the negative polarity strikes, the bright flash goes up. The positive polarity strikes, the bright flash goes down. Now here's something to know. If you are a slow blinker, you would have missed everything in this video. This video is barely 0.3 of a second long, okay? Just barely 1/3 of a second. And as a consequence, you blink slowly, you would have missed all of this. That's how frequent and powerful lightning is. Amazing to see that, right? Okay, let's talk about that positive polarity stroke, just so you can see what it is. This is a graph that one of my students drew me a couple years ago, so I wanted to use it. We know that negative charges accumulate at cloud base, positive charges at the top. We know that on the ground, positive charges accumulate under the cloud, and the negative charges kind of get swept off to the sides because they're repelled because of the negative charges here. We know that the negative polarity strike, while the electrons come down, the return stroke goes back up. Positive polarity strikes, and one of the big reasons why they're 10 times more powerful, well, they often arc between the positive charge centers up here in the top of the cloud and the image charge, the negative charges that are on the ground. These strikes come down when we see them, 10 times more powerful. This is one of my favorite videos of them. This is shot at 1,000 frames per minute. This is a windscreen wiper right here. Watch these towers in the back. You would not see this. You would see, ready? 1, 2, 3, 4. You'd see those 4 return strokes. You would not see the beginning of that lightning strike. Amazing just to watch this happen. Let's watch it again here. Ready? Leaders going up. 1, 2, 3, 4. 4 return strokes in just a fraction of a second. Absolutely breathtaking to see that. So that is how your lightning strike works. All right, some review. Let's make sure you've been paying attention. Which of the following places is the safest place to be during an electrical storm? Well, I hope you watched all the myth or fact videos here because I'm going to bring them up again. Ready? Is it in your car, under a tree, in your house, on a golf course, or in a fishing boat? Now, I'm hoping that most of you have already gotten rid of on a golf course and under a tree. We've been talking about that. But what about being in a fishing boat or on your house or in your car? Well, the answer to this is definitely in your car. Your car behaves as a Faraday cage, which we explained in the myth or fact exercise, and therefore it's extremely safe. Now, if it's a convertible, that doesn't work. If it's a carbon fiber car, I don't know if it works. But if it's a standard car with a metal subframe and chassis, it's very safe. In your house is also very, very safe. But we have a rule in the Snodgrass house. If there's a thunderstorm nearby, we don't take showers or do the dishes. We don't do that because our house is full of copper piping, which has water in it, both of which are good conductors. And historically, people have been struck while doing dishes or taking baths because of the highly conductive properties of the conduit. But I want to talk about in a boat, okay? Fishing gets its own category, 8% of all fatalities. Please, please, please get off the lake, get off the ocean if thunderstorms are approaching. Another review question. What ingredient must a cloud contain in order to produce lightning? Okay, is it strong wind shear, ice, dust, or organic microbes? Now, hopefully you remember this just from a few moments ago. The answer is definitely ice. You gotta have ice. The ice helps build up the huge static charges that are eventually discharged when a lightning strike occurs. All right, we're ready to go on and finish up this lecture by talking about thunder and other forms of lightning. Have you ever been taught to count between when you see lightning and hear thunder as a way to estimate how far away the lightning is from you? Well, I was taught this as a kid, and I've taught my children this as a kid. Taught them as kids when I was an adult. When my daughter was 4, we were sitting on the couch, and she was watching an episode of Bob the Builder. And there's a picture of Bob the Builder. Now, if you don't know anything about Bob the Builder, he has his own little kind of like claymation cartoon, I guess you'd call it. And he has a bunch of construction equipment, which are his friends. And he takes them out to kind of build stuff. Well, in one episode, there's a nasty thunderstorm that blows over a barn, and they go out to fix the barn. While out at the building site, Bob's friend, the crane, who's got the name Lofty, hears thunder and sees a distant thunderstorm. And Crane, naturally, being a large metal object, is worried and asks Bob what to do. And Bob says, well, hang on, Lofty, let's listen. So there's a lightning strike, and Bob begins to count. And the way he counts is 1 elephant, 2 elephant, 3 elephant. He's basically trying to count out seconds. Now, when I learned it was 1 1,000, 2 1,000, whatever, Bob counts elephants. Bob got all the way up to 8. And at that moment, he turned around to the crane and said, well, Lofty, not too much to worry about just yet. The lightning is still 8 miles away. And my little 4-year-old looks up at me, and I look down at her, and she starts to shake her head, telling me no. And I've never been more proud as a father, because my daughter understood the bad science that Bob the Builder was teaching. 2 problems. 8 miles away is not far enough away. Lightning has been known to strike up to 30 miles away from a particular location. In fact, the longest lightning strike ever observed was 199.5 miles. The rule is get about 30 miles away, and that's when you're starting to be much more safe. Secondly, when you count, you got to understand something simple about the speed of sound. This is what Bob got wrong. Okay, ready. When lightning strike occurs, here it is. It heats up the air right around the bolt to 54,000 Fahrenheit. That's 30,000 Celsius. That rapidly expands the air, causing a massive pressure wave. And that pressure wave is what we hear. We call it thunder. Now, when the lightning heats up the air and creates that rapidly expanding pocket of air that's in the immediate vicinity of the strike, and it blasts that out radially, as it does so, it travels as a sound wave. And sound moves at roughly 750 miles an hour. Well, 750 miles an hour, let's put this into a unit that we can use here. I'm going to multiply this by the ratio of 1 hour over 3,600 seconds. So my hours cancel out. If I divide 750 miles by 3,600 seconds, I basically get this, 0.2 miles per second. Which means if you go outside and shout, your voice in 1 second will travel 0.2 of a mile. Now, let's put it into something a little bit simpler here. The speed of sound is 1 mile every 5 seconds. Now, what does all of that mean? Well, here's the end of the story. The very next episode that we watched of television that evening, which it was storming in Champaign, Urbana, which was why we were watching TV, was an episode of the Berenstain Bears. And in that video, Sister Bear, in this episode called Count Your Blessings, was terrified of a thunderstorm. And Papa Bear said to Sister Bear, well, next time there's a strike, let's count. And so he did. There was a bright flash, and they all counted together as a family. And Papa Bear was only able to get to the number 5. Now, I'm watching the show with my daughter. I'm staring at the TV, hoping that the Berenstain Bears get this right. And Papa Bear looks down at Sister Bear, and I look down at my daughter. And Papa Bear says, you see, Sister Bear, the lightning is 1 mile away. And my little 4-year-old looked up at me. She's now 8, by the way. But she looked up at me, and she nodded, because she knew that Papa Bear got it right. Way to go, Berenstain Bears. Oh, by the way, living in a treehouse is the absolute last place you want to be in a thunderstorm. But at least you can count. I'm proud of that. All right, let's get into more of the stuff about thunder, all right? Here's some notes I want you to take down. Now, a flash of lightning can be seen but not heard. And historically, we've called that heat lightning. We can see distant thunderstorms, but never ever hear their thunder, and there's a few reasons why. When the lightning bolt produces a sound wave, well, sound naturally dissipates with distance. That's why you can't hear people shouting at you from great distances. The second thing is this. The Earth is round, and therefore as the sound wave travels, the curvature of the Earth can actually make the sound wave go right over the top of your head. So we have these two competing effects here. And as a result, the farther you get away from the lightning strike, the less of a chance you are going to be able to hear it. Now, in addition to counting, as you see down there in the bottom right, you can listen to the pitch of the thunder to tell how far away it is from you. If it's a brief, very, very loud, high-pitched crack of thunder, like bam, then you're talking about a close proximity strike. I think you would naturally conclude from what you just heard that that's the case. But if it's a long, echoey, less loud, low-pitched, deep rumble of thunder, well, you're basically getting the thunder from a very distant lightning strike where only the longer wavelength sounds are surviving because they're echoing off of everything. So you can use that as a metric as well. But thunder is simply caused by the heating up of the air. When I was a kid, I used to think it was because the lightning cut the air in half and it clapped back together. That's not how it works at all. It just spreads the air out rapidly, creating a huge pressure surge. By the way, if you were standing next to this pressure surge when it happens, in the immediate vicinity of the bolt, the sound wave travels at around, it's supersonic, and it would knock you off your feet, just the sound wave alone. Pretty amazing to see that. Okay, let's briefly talk about some other forms of lightning, and we'll wrap this up with a quick discussion about safety. Here we go. Other forms of lightning. One is called St. Elmo's fire, which I believe is the patron saint of sailing. You see tall objects just before they're about to have lightning strike. Well, we can often see them shooting out sparks like this. Do you see it? You see these tall objects like cell phone towers or power lines or the masts of ships would often shoot out little jets of sparks. That's actually the positive streamer responding to the negatively charged cloud base. They were just nicknamed St. Elmo's fire. We've even seen St. Elmo's fire on the leading edges of aircraft. This is not a doctored image. This is real aircraft here, showing you the electricity kind of spreading across the front of the plane as it penetrated into the kind of cloud where it was electrified. Amazing to see that. I've never seen ball lightning, but it is real. It's been described to be about the size of a softball up to the size of a basketball. A distinct feature is that it stinks. It smells like sulfur. It can burn for several seconds. It can roll around and bounce. It can burn its way through walls and through all sorts of things. It's claimed that around 1 in 500 people in the United States have claimed to have seen ball lightning. I have never seen it, but it is a documented natural scientific phenomenon. What we think it is we think it's a ball of plasma. So that's kind of a fourth energy state. We think it's a silicon plasma when you have lightning that strikes very silicon-rich soil. But that study was largely inconclusive on that being the primary source. I'm going to talk about these other types of lightning, and I don't know much about them. But above the storm, we often get what are called blue jets. You see them here. We can get sprites, which are these features, and elves, which you see these big expanding discs. Now, I don't know much about them, so I can't teach you more than what's in the book. So we're just going to show you some examples. Check out this video here of a blue jet. It's going to be right over here. Watch, I'm going to try to pause it. There it is. Oh, I did it. Do you see that right there? That was on top of a thunderstorm. So we're looking down from the space station here, okay? And what we're seeing this blue jet shoot up from the top. Now what has probably happened is underneath this, a big positive polarity strike went down. And this was just a reflection of it, the expression of it up. Blue jets, absolutely amazing. Just wanted to show you some video evidence that these things exist. Okay, I do want to show you one last video here. This is one of my favorites, sent to me by one of my former students, Michael. What he captured is my favorite type of lightning. I call these anvil crawlers, and they are just amazing to see. They kind of go right along the underneath side of the anvil of a thunderstorm and along what we call the screening layer, where we have this distribution of charges, and as they travel, they can move great distances. The world record was set by one of these, and you can see it in the inlaid graphic in the bottom right. In Oklahoma, 199.5 miles long, the same lightning strike. Incredible to see that. Well, here's the last thing I want to finish up with. Ready? What do you do if you think you're about to get struck by lightning, and how will you know? Well, because the electric field beneath the thunderstorm, right in the vicinity of a strike, can get up over 1 million volts per meter and up to 3 million volts per meter, you will feel it. If you have hair, long hair, it'll stand up on end. Even if you don't have hair, you'll feel a tingling sensation. It's incredible. The power buildup, the electric field buildup is enormous. What do you do? Well, I'll tell you this. Don't lie down on the ground. You may think, I got to be the flattest object I can be. No. Crouch down low on the balls of your feet. Hug your knees and stay there until the sensation goes away. Do not lie down. Because if the strike hits the ground and travels through the ground, well, if you're lying down, your body covers a large area, and one part of your body may be at a higher voltage than another part. Therefore, that voltage difference will drive a current through your body, and you'll get struck. But if you put your feet together and stand very put your feet together and stand very near to the ground, you will minimize the probability of you getting struck. Don't run. Don't run if you're in an open area. Now, if there's a car nearby, run to the car, get inside. If there's, get out. But if you're in an open area and you feel the sensation, crouch down low to the ground, hang on to your knees, and maybe it's a good time to start praying, okay? Now, do this until that sensation goes away. Now, why not run? Well, you can't see the electric field buildup. You may actually run yourself right into where the greatest buildup is. The extra height that you add could complete the circuit, and you could become part of the lightning strike. So stay put. If you're in an open area, do not go find the nearest tree and hide underneath it, okay? Please don't do that. If there's a car nearby, get in it. If there's a shelter nearby, like a house, anything, get inside that. That's much safer. But if nothing's nearby, crouch down low. And one of my students sent me this picture. This was a longest drive marker at a golf tournament, and it was struck by lightning and blew out to the ground. I don't know. Maybe it was because this guy cheated. Who knows? But hopefully now, that was a long lecture, but hopefully now you feel a whole lot more familiar about what lightning is, how it forms, how clouds become electrified, and what it can do. Plus, we now finally get what thunder is. But with that, I'm going to wrap this one up.